I made $30, but they lost. Yeah. All right. So, did anybody have questions about the homework? Pretty easy. Nothing here. Nothing was bad. Notice that your next homework, I changed the due date. It'll be a week from today, because I don't know how much we're gonna get to today, and I haven't finished making that assignment yet. I don't want to force you to try and get it done by Wednesday, because I think that the next topic is probably going to take, today and Wednesday, and then it'll be due Monday. And I'll post that assignment either tonight or tomorrow, so you have plenty of time to work on it. But it's possible that you won't be fully equipped to complete it until Wednesday. Okay. So there's nothing, no questions? All right. So I guess what we will do is we'll start with, I'll kind of review what we talked about last time real quick. What a nightmare. If it starts doing this, then I'll just turn the light back on. Yeah, maybe I just should do it. Is this what I did last time? Did we have this shadow last time? This? Maybe I had it further back. Yeah, like that. Alright, this will probably be fine.
The camera itself would come with a powerful enough light,
You would think. This light's like really bright, but this should be fine. Alright, so last time we started talking about sinusoids, where, it's still doing it. Whatever. So this is kind of the gist of your homework, where from any two of the like points on the waveform, if we measure that time period, that's our period. That's called our period t. And then if we count how many periods we have basically in a second, that gives us our frequency f. But basically t is equal to 1 over f, and vice versa. If we solve for f, that's equal to 1 over t. That's basically just because my period is telling me how many seconds I have per cycle, right? So this is t is in seconds per cycle, but we usually just say seconds, right? Still doing this? And then if I do 1 over that, that would give me cycles per second, right? That's hertz. That's what hertz is. So frequency is in cycles per second, or also known as hertz. All right. And then, we talked about how standard waveforms, we see them in the, the form of, let's say, v of t is equal to some magnitude or some amplitude, v max, times the sine of 2 pi ft plus a phase shift. We talked about this. 2 pi f is equal to omega. Basically, this is a time varying signal, and if we plug in a frequency here, then that would produce a signal based on that frequency. It would, we talked about all this stuff, and then we talked about phase shift. We're going to talk a little bit more about phase shift today, which basically, when we talk about phase shift, we might be talking about another signal. So let's say that this nice looking green waveform here, or the dark green waveform, is my input, or and that signal, that sine wave, has a phase of 0 degrees, right? I might have another signal let's just draw some points here. Might look something like this. and that signal, its peak is basically what we call out of phase from the input, and that's important. How did you want to help him real quick? Move the table and stuff. And so I think I talked last time about how we can convert between this phase shift in degrees and converting between the phase shift in degrees and a time delay in seconds, basically. Because obviously, well, maybe not so obviously, one cycle in degrees is equal to 360 degrees. That's kind of like what we see on the unit circle, right? We start at 0, we make one full rotation, and that's 360 degrees, or 2 pi radians if you're in radians, right? So basically, when we're talking about phase shift, we usually talk about it in terms of degrees, but that's not super helpful in real life. We might be able to measure the time delay between the peaks of these two signals, and then we would want to know, okay, what's the phase based on that time delay? Okay, so we can go back and forth between phase shift and time delay, and I'm going to talk about that right now. Okay, so if I have a phase shift phi, right, I want to know what would that result if I had, let's say that this was out of phase by 90 degrees, because it's out of phase by 90 degrees if I draw it like this. If I had a phase shift of 90 degrees and I wanted to convert that into a time frame, basically what I would do is I would take my phase shift and I would divide it by 360 degrees, because now I'm getting a ratio of what fraction of that full cycle is my phase shift. And then I'm going to multiply that by my period t, and that will give me my time delay. Okay, so let's look at an example. Basically, 90 degrees is 1/4 of a period, right? So if I were to take 90 and plug it in for phase and divide by 360, that would give me 1/4 times t, my period. So let's put some labels here to make this more clear. This is my phase shift. Sometimes it's called a phase angle, same thing. This is my period, and this is my time delay. And I think it goes without saying, but I'm going to say it anyways, you could rearrange this equation for phi so that if you knew the time delay, you would get phi, right? And so if I wanted to do that, I would basically divide by t so that I get td over t, right, times 360 degrees. That gives me my phi, right? Any questions about that? No?
James,
Yeah.
what is that 90 degree underneath P?
That's the phase shift. That's telling me it's out of, basically if two signals are right on top of each other, their peaks align, those two signals are called in phase. They have a phase shift of 0 degrees, right? It's basically the distance between like points on two waveforms in AC. These two signals are out of phase by 90 degrees. That means that this signal is basically shifted 90 degrees, or 1/4 of a cycle from the reference signal. In this case, we're not looking at a circuit, but it might be like this light green waveform is my output. Let's say this is my V out, and the dark green is my input, V in. So my V in would have a phase of 0 degrees, and my V out would have a phase of 90 degrees. And that's telling me that it's shifted 90 degrees from my input. Okay, that's important in AC. We're going to be talking about the magnitude, which is basically the amplitude, and the phase quite a bit. So this is my V max, and this is my negative V max, or my amplitude. Yeah.
A couple questions about phase shifts. So the time delay it's just always going to be positive, correct?
No.
Okay.
No. So that's something I'm going to talk about today. So when we're looking at AC signals, basically we can talk about the two signals in terms of the phase shift, but if we don't know the sign of the phase shift, we don't know which way it's shifted, right? So another signal might be, have its peak over here, 90 degrees the other way, right? And if I say 90 degrees to you, then you're not going to know which way it is. And so basically, when we talk about these types of signals, this first signal that I drew, what we would say is that this signal leads by 90 degrees. And that's why my phase shift is positive, okay? It's leading the other signal. What does that mean? It means that this peak happens earlier in time, right? It happens at an earlier time. Oh, actually, I'm sorry. I had it right originally. Let me just get to a new. I wanted to talk about that, but let's do it on a new sheet of paper. Because when it happens earlier in time, you call that leading, and when it happens later in time, you call that lagging. And that's going to be important when we get into doing some stuff with these circuits. But for now, always basically look at it as time shifts that don't have, or not time shifts, but phase angles that don't have any magnitude. There's no sign associated with them. And when we get into associating a sign with them, that's when leading and lagging is going to matter. So I might, let me just draw. We'll just do another example. All right. So let's say this is my input. And then let me draw another signal. It's right here, maybe. All right. All right. So if I were to have these two signals and I was to look at these signals, if I wanted to measure my time delay, let's say I was going to do this in LT-Spice, and I probably will do this in LT-Spice in a second. I would basically look at the two peaks. I would look at the peak of this signal, and I would look at the peak of this signal. And I would measure what is that time, T. That would be my time delay. And I was just talking about how I could calculate my phase based on that time delay by TD over T times 360 degrees, right? So when you're looking at it, obviously when you calculate the phase, you're not going to necessarily know whether it's going to be positive or negative. This is where it's important to analyze whether V out occurs later in time or earlier in time. In this case, the peak in V out occurs later in time than the peak in V in, right? We see that. So V out would be lagging V in. So let me write that. V out lags V in by T, or phi, or you could say V out lags V in by the time delay. Typically, it can go either way, and it depends on the context. If you're sitting in the lab looking at an oscilloscope, you're not going to know the phase angle. You're going to know the time delay. So you're going to say V out lags V in by a couple microseconds or by 3 milliseconds. And then you can convert that if you know your period. Say it's 3 milliseconds out of 4, then you know it lags by 270 degrees, right? Because that's 3/4 of a period, and a period is 360 degrees. Okay? That's two ways that you could say it. There's another two ways that we could say it. We could say V in leads V out, right? That's also correct. Or V in leads V out by TD. All right? Does that make sense to everybody? The peak in V out occurs later than the peak in V in, so V out is lagging. or the peak in V in occurs earlier than the peak in V out, so V in is leading. Okay, this is going to be, and this doesn't just go for voltages. Okay, so what we'll see when we get into these circuits with capacitors and inductors is that we'll look at the voltage in the circuit and we'll look at the current flowing in the circuit, and we'll see that the current will lead. Well, it depends on how many components. So a purely capacitive circuit, if you just had capacitance, which that will never happen in real life, but if you ideally just had capacitance in a circuit, the current would lag the voltage by 90 degrees. Okay, and that's because, the voltage will lag the current because capacitors resist changes in their voltage. Okay, so the voltage lags. Inductors resist changes in their current, so the current will lag by 90 degrees. But that's assuming you only have inductors or only have capacitors in the circuit. In any real circuit, you're going to have some capacitance, some inductance, and some resistance. So you'll get some combination of the three, which will result in, say, the current lagging by 75 degrees rather than by 90 degrees. But you would still say that that's an inductive circuit because the current is lagging. Okay? This is all just terminology right now. But we'll see some examples today and Wednesday. What's your question?
So, if the current is lagging, then it'd be an inductive current. But if they end up like
An inductive circuit.
Inductive circuit. Sorry, an inductive circuit. So if they end up like just canceling each other out, and it ends up being zero, what would that be in that case?
That would be a resonance circuit. Okay. So when the inductive impedance and the capacitive impedance cancel each other out, that happens at some frequency, and that's called the resonance frequency. And at that point, there's no leading and no lagging, and you get the maximum power. Okay? You know power is equal to voltage times current?
Yes.
We've talked about this. P is equal to V times I. Right? So it's the same thing with AC signals. If I take let's say that instead of V out, let me write this in purple and call it I, and I'll just sketch the signal in purple too. Okay? So what happens if I'm trying to find the If I'm trying to find the power here, I'm going to multiply my V in signal by my I signal, and I would find the power, in the circuit, or the power that's supplied to the components in the circuit. If my V in signal and my I signal are perfectly in phase, at every point on the curve I will get a positive value for my power, okay? And that would be because, so let me draw that. What would that look like? I guess I didn't need to draw it up there. Say that I have this happening here, right? And then let's draw my axis like right there. Okay? When I multiply V times I at any point here, I get a positive number. When I multiply V times I at any point here, I also get a positive number because they're both negative, right? So my power waveform is going to look something like this. It's going to be, right? It's going to be the voltage times the current, where it's always positive. If we get negative power, that means that power is not actually being supplied. And then that's wasted power. And that's what happens when these signals are out of phase. Okay? So we're going to have points where, like, from I guess, here to here, on the entire positive cycle of the input, then the current and the voltage are both positive. But then we get this little time period where my current is positive and my voltage is negative. Now, that results in negative power, and we don't want that. So ideally, you want to operate in resonance to maximize power, because that's when your two signals are in phase with each other. And that's what we see down here. So a lot of times you'll hear about, maybe you've heard of load balancing before. Load balancing is trying to maximize that power that's delivered to our load by keeping everything in phase. But if you have unwanted inductances or unwanted capacitances in your circuit, they cause these phase shifts and your power is not maximized. Does that make sense? At least like hazily? Yeah.
So in a case where they're exactly phase shifted like 180 degrees and they're exact opposites of each other, would there just be no power put into the system at all, or would it the circuit not function?
So you're saying if my voltage and my current were out of phase by 180 degrees?
Yeah, exactly. Exactly 180 always
Like it's always negative.
yeah. Or it's
Yeah,
always-
ideally you would have no power delivered to the load, but
Okay.
I don't think there's such a thing as a circuit where nothing would be delivered to the
Yeah.
load. You would never have the current out of phase by more than 90 degrees in either direction.
Right.
If it was getting to the point where it was out of phase by 180 degrees, something would be wrong.
Right.
Okay.
I was just curious.
But yeah, you're on the right track. That is what would happen. Yes.
Secondary question about phi. Is it basically not relevant when we have different periods for our waveforms? Because if they're
True.
different, okay, if
True.
if they're of different periods, then phi is like, well, they can't really match up perfectly anyway.
Right. So that's the thing. When we're looking at these circuits, especially in this class, I mean, there are mixed signal circuits out there. You'll never analyze phase shift, time delay, or any of the signals unless their frequencies are the same. And if their frequencies are the same, then their period are the same, right? So this class is all about linear circuit analysis. These are all linear circuits, so their frequencies are going to be the same. Basically, let's say I had, like a little, I don't know, a little RC circuit or something, and I'm using a sinusoidal source, right? If this signal is going to have some, let's say it's V cosine of 2 pi ft, okay? The frequency of the signal at this point is going to be the same as the frequency of the signal at this point. The frequency is not going to change. No components can cause the frequency of that signal to change, okay? The phase, however, will change based on the components in the circuit, so that's why we talk about phase. And what we're going to get into today, and probably, maybe not today, but definitely Wednesday, when we analyze these signals, we don't always look at them in this form. Actually, we never look at them in this form. We use complex numbers, okay? So this is where complex numbers get involved, because we end up with basically resistors, which have an impedance of R, and we end up with capacitors and inductors, whose I told you already, their impedance depends on the frequency in the circuit. And so we separate those impedances based on whether or not they're frequency dependent. And that's where you get, your real part is your impedances that aren't frequency dependent, and your imaginary part is the frequencies that, or the impedances that are frequency dependent. And when we go into this new domain where we're looking at complex numbers, we use what's called a phasor to solve these circuits. And a phasor is basically, I'm going to represent this signal, but I'm only going to represent it by its voltage, amplitude, and its phase angle. And so this right here is called a phasor. This is my amplitude, and that's my phase. And we don't care about anything else, because the only other variable here is time and frequency. And when we're analyzing these circuits, we don't care about time or frequency, because we're looking at the signal over time. We're not be plugging in values for t. If we wanted to, we'd go back here. But basically, when we're analyzing these circuits, and we want to determine, well, what's the voltage amplitude here and what's the phase here? Because we already know the frequency. The frequency's not changing. So we use phasors, and it makes the math a lot easier. And I'll probably get into that next if anybody doesn't have any questions. Anybody have any other questions? Yeah.
I have a question. You were referring to these waves of Vn and Vout as a difference of 90 degrees. And I was getting confused here.
Well, not these waves, but the ones on the previous slide.
The previous one, the one on yeah, this one. So could you please explain that in terms of seconds?
Yeah, so my t, right? My t is the time it takes. That's called my period. That's how long it takes to make one full cycle.
Yeah.
Okay? One full cycle, think of it in terms of the unit circle, is 360 degrees.
Yes.
Okay? So if I say that my two signals are out of phase by 90 degrees, right? 90 degrees out of 360 is 1/4. Okay? So that means that in terms of seconds, this signal will be out of phase from the input by 1/4 of a period. So let's say that my t was 1 second. Let's say that it's 1 second. That means that my time delay would be 250 milliseconds, 1/4 of the period. Does that make sense?
Yeah, yes.
All right. Anybody else? All right. So let's go, and we're going to start learning about phasors. All right. So we already know that my time domain representation of a signal looks like this. It could be a sine, it could be a cosine, it doesn't really matter. It all just depends on... so like the textbook, I think that you'll probably use for 221 uses cosine. So if you guys are fine with it, I'll just use cosine from now on. But SPICE has a sine wave. So if you're going to use cosine waves, you have to remember that 90-degree phase shift. So I can use sine waves and it'll make SPICE easier, or I could use cosine waves and it'll make 221 easier. I don't know what you guys prefer. Huh?
Cosine.
Just do it in terms of cosine?
I mean, just add 90 or subtract 90.
Yeah, so just in case anyone's lost on what I'm talking about.
I think that also.
Hopefully if you did the homework, you're not lost. What did you say?
I said I think that would be better because that would also help us practice shapes.
Phase shifting?
Phase and
Well, because like say you have a cosine wave with a 15-degree time delay. Now you have or phase shift. You have to account for the 90 degrees in SPICE and the 15 degrees. Okay, so let's just take a look at what that might look like. What?
I didn't realize that one of these was cosine.
You didn't realize?
Yeah.
Oh,
I'm not going to make a change to it for that.
yeah, that's okay. Just leave it. All right, so DC offset. Let's go with 1. You know what? I'm going to call this V sine. All right, so I'll go sine. I'll go 0, 1 volt, and let's just go 1K because it's easy. I'll go dot tran 5 milliseconds. All right, so let's run it, and we'll see that this is a sine wave. Everybody knows that a sine wave starts from 0, right? Sine of 0 degrees is 0, right, in the unit circle. Cosine of 0 is 1, so if I wanted a cosine wave, I should have it start at 1 volt, right? So if I wanted to make a copy of this, I'll call it V cosine. And what I would do is I'd go into the parameters and I'd change the phi, right? The phi to 90. What the heck? Oh, I have 2 transients.
not a lot.
All right, so there's my cosine wave. Everybody sees that? And so I put 90 degrees, right, for my phase shift, which shifts it 90 degrees or 1/4 of a cycle to the left, right?
So the cosine would be leading, right?
The cosine leads the sine by 90 degrees. Is that what I said? Or did I not say that? I just said it's out of phase
Yeah, you
by
said
90
it.
degrees. Yeah, because I didn't want to start talking about leading and lagging. But so when a signal leads another signal, its phase shift will be positive with reference to that signal. If a signal lags another signal, its phase shift will be negative. Okay, so you're gonna have to keep that in mind. So when I put negative 90, it'll shift it the other way, and then the cosine would be leading instead of lagging, or sorry, lagging instead of leading. I'm all over the place.
So if it's positive, it's lagging.
No, I think if it's positive, it's leading. That's why I put 90 there, and the cosine's now leading the sine wave. If it's positive, it will be leading. It occurs earlier in time. The peak occurs earlier in time.
From right to left.
So this peak of the cosine is occurring here. I've just wrote a negative here. That's going to throw everybody off. What I have ran, right, my phase shift for my cosine is positive, which means it will lead my other signals. Okay, so it's leading by 90 degrees. It's occurring 90 degrees or basically 1/4 of a cycle before the sine wave. If I were to make this negative, it would occur 1/4 of a cycle after the peak of the sine wave. See that? All right? Yeah, question.
So basically, we're just reading, let's say we're looking at the graph from right to left, whichever one peaks first from right to left is leading, the one that peaks second or third or fourth or whatever from right to left is lagging.
It's from left to right.
Yeah, but it'll get a little dicey when you get further and further away, because then it might look close to this one and far from that one. So you're like, well, is it leading by 190 or is it lagging by 170? And so then you have to calculate it. Or you might not calculate it, you just use SPICE, but I'm probably going to ask you to calculate it. But yeah, so if you want to make a cosine wave, you just use the sine, because there's no cosine function in SPICE, so you have to use a sine and put it out of phase by 90. And then if your phase shift that you calculated is like 15 degrees, like I said, now you have to calculate the 15 in addition to the 90 and put that in SPICE. Okay, so whether it's lagging or leading, now you have to add or subtract 15 degrees from this 90. All right. Okay, so we're going back to phasors now. What was the question? Someone asked something about cosine? Oh, we just asked we're going to use cosines or sines. We'll just use cosines from now on.
Cosine would be more complicated, but it would be useful.
It will be because the textbook that they use. Let's just pull it up.
Is there a reason for that?
Why they use cosine?
Yeah.
It's just whatever they prefer.
Okay.
It could be that they just prefer for the signal to start at 1.
Yeah. I don't know if it's just like a standard thing.
Well, in that book, they literally mention it. I want to read it so that. Let's just go look.
Oh, you got games on your phone?
On my phone or on my computer?
Yeah.
I mean, I downloaded Rocket League, but I don't play it. I like it.
It's a good game.
Yeah, it's fun.
This is the textbook for 221?
This is the 5th edition of the book. Oh, by the way, Dr. Sabarinia asked me what book I'm using, and he said he would use the same book I'm using so that you don't have to spend money. But we're not using a book. But this book has a free PDF online, so I just recommended this one so that you guys wouldn't have to buy it.
You're a legend.
Why?
I was going to say, well, can you make this available on
I can post it on my website. This is like a really good PDF. It has like all the contents and all that. And I have the solutions.
Let's go.
Yeah, that's it.
But that's because I'm an instructor. You guys can't use those.
Totally.
What was that?
All right, let's get to phasors. All right, so somewhere in there it says something about.
What do phasors have to do with segments?
Was there a segue on there? I'm sure there's some AC something going on in there. I just want to see where they say, like, we're just going to use cosines for the remainder of this. A sinusoid is a signal that has the form of a sine or cosine. Yeah, we know that. So here they used sine, right? And then that's just talking about hertz. So if you want to know what hertz is, it's named after another guy. Periodic, blah, 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 frequency. See, they're still using sine. At some point, they switched to cosine. And then they're like, we're just going to use cosine for the remainder of the book. I'll post this book today so you can start using it as a reference if you want. These are going to be really important. This is basically showing you how you get from a sine to a cosine to a sine, and all that. Magnitude of the sine. We're getting there. See, now they start using cosine.
Oh, a little bit up.
Oh, did you see it? Did it say something?
A little bit right there. A plus B equals C cosine.
Where, this thing?
Yeah.
Well, somewhere it says we're just going to use cosine for the remainder of this book, but it could go either way. That's all I was really trying to find. I don't want to waste too much more time trying to find it. No, it's fine. I mean, it's a good question. Why would we use sine versus cosine? There's really no reason. I think it just depends on the book. Like, this book references everything in terms of cosine.
I was just curious if it was like an industry standard that they only use cosine or something stupid like that.
I have absolutely no idea.
It says on the right side of your spreadsheet, in the green.
This?
Yes.
We use sine instead of cosine, then...
That's the right side.
No, it's not. I don't know where it is.
Okay, we'll find it at some point.
Yeah, well, when you take 221, you'll probably find it.
If you read the book.
Well, Sabrina is teaching over the summer. You guys are taking over the summer? Who's taking over the summer? Yeah, okay, so you'll be using this book, hopefully, if he takes my advice. He might be like, nah, I don't like that book. But he asked, so. Okay, back on the farm. So this is how we represent a signal in time domain. There's also phasor domain. Okay. All phasor domain is it takes the amplitude from here and it takes the phase from here and it puts them into one notation so that we get all the other garbage out. Okay? So phasor domain is amplitude, okay, first, and then they draw an angle, all right, and then they draw the phase in degrees. You will never write the time delay in a phasor. It will always be the phase angle, okay? You can find the time delay and then use the time delay to find this phase angle, but you'll never write 2 volts, angle, 2 milliseconds. You'll never see it that way. You'll have like 2 volts, angle, 90 degrees, okay? So this is how a phasor is written. So I would literally just take this directly from there and this directly from there. And that would be my phasor for that signal, okay? Yes?
Will the phasor will the angle ever be given in terms of pi? Or will it always be given in degrees?
I've never seen it in terms of pi. It's almost always in degrees. But if for some reason your brain just operates in radians and you are like, oh, that's out of phase by pi, then just know that that's 180 degrees. Like,
Okay.
I don't know. I hope that the general consensus is that degrees are easier to like think about. But if you're that person who thinks that radians are just way better,
I just came out of a
Probably the same person
physics and math
like current
classes.
dividers.
oh yeah.
I feel like radians are easier only just because I just came out of a bunch of physics and math classes. But if I wasn't, I would like degrees a lot more.
I mean, degrees, I don't know. When I was doing the unit circle, I always memorized everything in terms of degrees.
Degrees are bust. Get out of your radian degrees.
Nah, you guys are fine if you like radians. But you have to do degrees here, so it's not really going to benefit you.
I was just waiting for you to say you're wrong, but
No, you're not wrong. I mean, it's fine. Just, I like degrees better.
It's just not right.
Okay, so if I was going to take like a signal, let's say I had a sine wave. Let's say it was, 5 cosine of 2 pi times 1k times t minus 81 degrees or something. Let's say that's my signal. If I were going to write that in phasor, all I have to do is look at the amplitude and the phase, and I can go, okay, so 5 angle negative 81 degrees volts. That would be my phasor for that signal. Okay, so you write the 5 angle 81 and then you put the units on the outside. That's pretty standard. Okay, this was just an example. Typically, our input is going to be 0 degrees. That's because that's what we're referencing everything from. It's going to have, so typically you'll see, let me draw another one. You'll see something like this. It'll be 5 cosine of 2 pi times 250k times t. There won't be a phase there. And that would be my input signal. And if I'm going to write the phasor for that, it would just be 5 angle 0. Okay? And note, right, when there's no phi here, if it's just some term t and then there's no plus phi, like over here I have minus 81, here I have nothing. That means that my phase angle is 0. And so if this is a cosine with a phase angle of 0, right, it's going to look just like this. It's going to have its peak right at 0, like what we would expect. All right? And then, again, let's say I connect some RC out here. Then I might get, some phase angle on my output. And then when I plot the two signals, we'll see that phase shift. And that will be referencing this input as my 0 phase. Okay? So...
Does that phasor notation account for the 250K?
So we don't. So basically, at any point in the circuit, the frequency is going to be the same. So rather than writing it over and over again in our math, we just use phasors to get rid of it because we know it.
So we just assume it's the same all the way through and use. Okay.
It will be the same. It will never change. So I kind of have to draw circuits to get into like more what's going to actually make sense. But let's just say I had like an RC circuit with an AC source. Note that RC circuits in this context do not work the same way that they work in the context that we're used to now. Okay, so these are AC circuits. This is completely different. Our source is not a pulse. Our source is a sine wave. Okay, so it's actually going to be a lot easier. It's going to be a lot easier because they're just going to act like voltage dividers. Again, this is going to have an impedance, that's going to have an impedance, and we're going to calculate the voltage using the exact same equation, except now we have to account for phase, so we have these complex numbers. But this is going to be a lot easier than the RC and RL circuits unit, because I feel like that was probably everybody's least favorite part of this class. This will be a lot easier than that.
I don't know, that was pretty rough. I don't like that.
You liked RCs and RLs? I feel like everybody hated them.
I liked everything.
I feel like everybody was coming to class miserable, like, oh my gosh, we have another quiz on this stuff. Maybe I'm wrong. Maybe you guys love them.
The thing that I disliked the most was like plotting all the points because it was just like really
Tedious?
I was
Yeah, but it's the only way.
On this last homework, I have just a page just for the calculations.
Yeah, I mean, that's good.
Entire page just for the calculations.
Didn't you join this major for the math?
No.
I joined it for the math.
It's for magnets. Everyone joins the major for magnets.
For what?
For magnets.
That's not why I joined it. I just like circuits. All right, so let's say we were looking at this RC circuit. That would be my V in, my V out, just like we're used to seeing, okay? Don't worry about the RC yet. I'm just trying to get this point across. If my V in was this 5 angle 0, let's say 5 angle 0, let's say that this just turned out that the impedances were equal in AC at a certain frequency. Then my output will be 2.5, right? My magnitude will be 2.5, angle, who knows what. We don't know that angle, but we're going to determine that using math. Okay, so this is like the motivation here. It's going to be similar to DC, but instead of just looking at amplitudes, we have to take into account phase because it matters. Okay, so now without going, does anybody have any questions about this before I go into actually how would we solve this circuit? How would we determine that phase? Questions? Yeah. Okay, so there's a couple. I'm just saying, assume that this was a voltage divider where the impedance of this resistor is equal to the impedance of this capacitor. Then we would get 2.5 amplitude out. Well, we don't know what the phase is because that's going to depend on the capacitance and stuff. But I'm giving a motivation. We're going to have an input signal that's going to have no phase, and we're going to have an output signal that's going to have some amplitude and some phase depending on the component. So that's what we're going to be doing in this unit. We're going to be looking at these circuits similar to how we did in DC, but we're going to be solving them in AC. And this is going to be like the first week to week and a half of 221. So if you guys can hammer this down now, the first week and a half of, well, if you're in the summer, it'll be a week and a half. If you're in the real class, it'll be probably like 2 or 3 weeks. This will be very easy for you when you get into that class. Yeah.
If the cosine is just a phase shifted sine wave by 90 degrees, how come in that first example it's just negative 81? Should you add or subtract negative or add or subtract 90 degrees from that?
I just threw some random signal there. That's nothing.
Okay.
Well, yeah. Well, so if I wanted to plot this in Spice, I would have to take it as a sine wave first because Spice only has sine waves. I'd have to shift that by 90 degrees, right? And then I would have to subtract 81 degrees from that, which would end up being 9 degrees basically. It's going to be positive 90, which makes my cosine lead. I'm doing it how I would do it. Okay? So it's going to be positive 90, which is going to make my cosine lead, and I'm going to subtract 81. So at the end, it would just be sine of 9 degrees would be my phase if I want to put that in Spice. That's what you're asking, right? You take into account the 90 first, and you subtract the 81, you get 9. Okay? Yeah.
So, question: when we're just given the phase, I forgot. When we're just given the one with the angle, I forgot the name of it.
The phase? The
Yeah,
time delay?
Yeah, just the phase one, where it's just the one that's boxed.
The phaser.
Sorry, the phaser. How do we know if it's I'm dumb. Phaser. How do we know if it's supposed to be sine or cosine in those cases?
That's depending on the textbook.
Just depending on
The textbook says we're going to use cosine. So you just know if this is 0 degrees, it's cosine based on the textbook. So that's why I'm saying from here forward, would you rather me use cosine or sine?
Oh, okay, cosine. Yeah.
Okay, so I'm going to use cosine. So we will use cosine.
Yeah, that was just the surface way you didn't know that. Yeah.
All right. So if you see 5 angle 0, you know that that's 5 cosine 2 pi ft. That's what it is.
Okay.
All right?
Yes.
So this is how it's going to be in 221 also, if you use that book. I assume you're going to use that book. I've seen cosine more frequent than I've seen sine, which is kind of weird because Spice does sine. But all the textbooks I've seen, they like to use cosine. So I don't know why that is. I haven't worked with AC stuff in like any of my jobs. But there's got to be a reason for it. I assume they like cosines better. Maybe they have better properties.
Just because it starts with moving from.
That's what I'm thinking. But I mean, you could also argue sine starts at 0, so that's easy. I don't know. I don't know why, but well, I just signed the contract. All right. Any other questions before I move on? Because we're going to get into an example of solving an RC circuit in this domain. And RC doesn't matter now. It doesn't matter. The C and the R and the C. It's not going to matter because they're all just going to be treated as impedances, right? They're just resistors in the AC domain, okay? They're not going to be, you're not going to have to think about, is it rising, is it falling, is it going to shoot negative? None of that stuff's going to happen. It's going to be a sine wave on the input, a sine wave on the output, how far is it shifted, and what's the magnitude. That's what we're doing here, okay? Any questions about that? All right? All right. Everybody nice and motivated? We have 12 minutes, and then I'm giving the quiz. Quiz should be really easy today. If you did the homework, the quiz will be really easy. All right, so first and foremost, this is where the complex numbers come in, okay? So let me, maybe I should just, should I review complex numbers? You know what, I'll just do an overview of it today, and then don't worry about it, because I said this homework's not due till next Monday. Resistors, capacitors, and inductors all have impedance, like I said, right? We use Z to denote impedance, okay? So this, the impedance of the resistor is just its resistance, okay? All right? The impedance of the resistor is just its resistance. There's no complex part of it, okay? We're going to get into complex numbers right now, that's what I'm saying. But don't worry because that's not on the quiz, that's not on your homework until Monday, and we're going to go way more in depth on this Wednesday. But I want to give you an overview so that when you come to class next time, we can go right into it, all right? The impedance of a capacitor is 1 over j omega c, all right? So this is where we start. And we just know omega, right? We know omega is 2 pi f. So we can also say it's 1 over j 2 pi f c. Okay? Now note, right? If I say that this is 1 over j 2 pi f c, what happens if we plug in f equals 0? What is that impedance? If f is 0, it's infinite. That's f equals 0 is DC. So my impedance is infinite. That's why my capacitor acts like an open in DC. Okay? What if I plug in F is some huge value? What would happen to my impedance?
0.
That's why it acts like a short at really high frequencies. Okay? That's the capacitor.
What's J?
What?
What is J?
J is the... Okay. Yeah, I forgot you guys don't know what J is. J is I in complex numbers. Well, we use J because I is for current. Okay? So it's just J is equal to the square root of -1. Just like you're used to in complex anything. It's just I. But we can't use I because then it looks like current. So they use J in engineering.
Can't you just use capital I for current, little I for...
They use capital I for large signal AC current and little I for small signal AC current. But this stuff all goes this is way beyond this class. Just so you know, J is just I. Okay? My inductor is j omega L. This is easy to remember, right? 1 over j omega C, j omega L. And if you forget, think about this. It's an open. The capacitor is an open for low frequency, which is basically DC. So if you forget, you go, oh, if I put the F on the bottom, that's 0. Impedance is huge. It shouldn't be hard to memorize, though. Again, omega is just 2 pi f. So I could write this as j 2 pi f L. All right. And again, if I plug in 0 here, f is 0, what is my impedance? It's 0, which is a short for DC, right? It just acts like a wire, exactly what we talked about. And then if I plug in a large frequency, it acts like an open. This is the things we were talking about, but this is why, okay? So now that we know these things, we're going to go into how I solve one of these circuits, basically. Okay, if I wanted to solve one of these circuits, let's just take again, I don't want you to think about these circuits in the context of how we thought about them when we just did RC and stuff like that, because this is completely different and it's so much easier. Okay, so this is going to have, let's say this is a 1 microfarad capacitor, and this is a 1K resistor, and we have V in and V out here. Right off the bat, what we do in these AC circuits is we just get all the details out that we don't care about. Okay, so what they do typically is they'll redraw this circuit, and they'll just draw it like a voltage divider, but these little boxes represent impedances. Okay, so for the resistor, it's just 1K. It's an impedance of 1K. Also, impedance is in ohms, so all of these are ohms. So that would be 1K. Now my capacitor, I don't know my frequency, so let's just say that my input is, again, 5 cosine of 2 pi times 1K times T. So my F is 1K, right? So if I wanted to find the impedance of my capacitor, I know that ZC is 1 over J times 2 pi times 1K times 1 microfarad, right? J 2 pi F C, right? That's coming from straight from the formula, okay? Let me do that real quick. Somebody else do it so we can confirm. 2 pi, don't worry about the J either. The J is going to stay down there for now. J 2 pi times 1000 times 10 to the minus 6, and I invert it. So it's 159.15 divided by J. Right? However, if I were to, I don't know if you guys are familiar with this, you should be, 1 over J, or 1 over I in complex is just equal to minus J, okay? So I could rewrite this as minus J times 159.15. Again, it's ohms. It's just impedance. So I would write right here minus J times 159.15. Okay, and now I have a voltage divider. I have a voltage divider with, 2 impedances. And I have my V in here and my V out here. What do I have, 5 minutes? Again, this is probably seemingly overwhelming, but it's really not that difficult. I'm going to go over it slower next time. I just wanted to overview it. Okay? So my input would just be 5 angle 0, right? All right? And so what I have here is I have 2 series impedances, and I can just add them. So my total impedance would be 1K plus minus J 159.15, or so that would be my total impedance. Okay. Now, does everybody remember that in complex, complex numbers, what we have, if we look at a complex number Z, it's basically X plus, well, I guess you might have seen it as X plus IY. Where the X is my real part and the Y is my imaginary part. Okay? So here, I have basically a real part to my impedance, and I have an imaginary part to my impedance. Alright? Now, the important thing here is that we need to get a phasor out of this so that we can actually solve this circuit. And phasors have a magnitude and a phase. Okay? So I'm just going to show the motivation for this real quick. 4 minutes I have. Let me see if I can do this. Typically in imaginary numbers, they talk about the real plane and the complex plane. So I'm going to draw it like this, where this is my real and my imaginary, right? Okay, so if I had, let's say I went out 1K, and then I guess my imaginary I'm going down by negative 159, and this is out 1k. What I end up with is this point, which is my number. That's 1k minus j159.15, right? Okay. Well, that's just a vector, right? It's just a vector that's pointing out to that point. And I can use some geometry to determine the magnitude of that vector by finding the hypotenuse of the triangle that it creates. And I can find the angle from the x-axis by doing, the tangent of the opposite over the hypotenuse, all that good stuff. I can derive that next time if people are interested in it. But basically what we end up with is if I take my real squared plus my imaginary part squared, and I square root that, that gives me my max, my magnitude basically. In this case it's not a v, it would be z. But that's my magnitude. Okay, so magnitude, let's just take x plus jy, all my off the screen. So I'm at x plus jy, right? That's my standard form of my complex number. So if I want to find the magnitude, it's the square root of x squared plus y squared. Okay, and I can derive that geometrically. Okay, it's just the hypotenuse, right? A squared plus b squared equals c squared. I'm trying to find c, so I square root both sides. That's all I'm doing. And then my phase comes from the fact that the tangent of my angle there that I just drew is equal to opposite over adjacent, which in this case would be y over x. So if I wanted to find phi, I would tan inverse both sides, okay? So my equation for my phase is the tan inverse of y over x. Okay, so that's my magnitude equation. This is my phase equation. And don't worry, I know I went over a lot of this way too fast. I'm not expecting you to do it by Wednesday. I already said I just wanted to give an overview of this. But basically now, using this total impedance that I found, I can take my real and my imaginary, and I can plug them into these two equations, and I can obtain a phasor for my impedance. Okay? And we know that, V is equal to I times R. Okay? So if I want to, let's say I want to find the current flowing in this circuit. I would go I is equal to V over R, and then whatever phasor I come up with for my impedance, I would just go my voltage phasor over my impedance phasor, and I would get my current. So it's just using Ohm's law again, doing voltage dividers again, all the stuff that we're used to, except these complex numbers come into play because of the phase shifts. Okay, any questions before I give the quiz? This is not on the quiz, and we're going to talk about this more on Wednesday.
In simple words, what is it?
It's resistance. Resistance is basically the resisting of the flow of electrons. Impedance is the exact same thing, but we just in AC circuits and not in DC circuits. So it's just think of it as resistance. Okay? All right.